All right, so today we'll start the subject of electrostatics. Okay, so the next 4 chapters are the subject of electrostatics. What we'll study in these chapters is charges, and you know that charges create electric fields and all the effects of that. Okay. So electrostatics is a subject where you're not letting the charges move. Okay. And we'll study the electric field around it. And so we'll study various aspects of that in the next 4 chapters. And then what we'll do is we'll get the charges to move. Okay. And when the charges move, you learn that they produce electric fields, and in addition, they produce magnetic fields as well. Okay, so that will be after we study electrostatics. So right now in the next 4 chapters, we'll keep the charges stationary. Okay. All right, so let's get into the details. Okay, we'll talk about electric charges, insulators and conductors, Coulomb's law, and charge quantization. Okay. All right, so here are some everyday material. So what these materials are, they're electropositive materials. What they're willing to do is they're willing to give up some of their electrons if somebody asks them nicely. Okay, these guys are willing to take electrons. So, for instance, if you take a rubber balloon and brush it against your hair is willing to give up electrons, and the rubber balloon will accept electrons. So, your hair will become positively charged, and the rubber balloon will be negatively charged. Okay? Now, the rubber balloon grabs a very small fraction of the charges. Okay? And you guys have experienced this. You walk across a carpeted floor and you get charged. Okay? And during the summer, when there's moisture present in the atmosphere, the charge will leak away. Okay? But in the winter, when the air is dry, the charge doesn't leak away, and then you go and grab a door handle and you get a little spark. Okay? So you've experienced this kind of stuff before. Okay, let me just show this to you, illustrate this to you. All right, so normally all objects are neutral. So here's a wool sweater that is neutral. Okay, and again, okay, so a wool sweater is willing to give up its electrons, and a rubber balloon will attract electrons. So when we rub this rubber balloon against the wool sweater, this will become negatively charged and that will become positively charged. Okay. So here we go. Okay. There we grabbed electrons from there. Okay. And then if you let go, they'll attract each other. Okay. What was that about? Okay, so now we charge these two guys, and they should repel each other. Okay. All right. So that's how you can charge objects. Okay, so that's how we charge objects in an everyday life. Okay. Okay, so we've studied all of this, and we found that there's only 2 kinds of charges in nature. Okay. And so we can call one positive and negative, or whatever you want to call, charge A and B and stuff like that. Okay. And what we find is 2 positive charges, 2 like charges repel each other, and unlike charges attract each other. Okay. All right, so let's say this is positive charge 1, positive charge 2. This guy repels him with a force of 10 newtons. What does this guy do to him? Right, that's Newton's third law. Newton's third law says if this guy repels him with a force of 10 newtons, this guy will repel him with an equal and opposite force. If this guy attracts him with a force of 10 newtons, this guy does the same, attracts him with a force of 10 newtons. And that's why we haven't drawn those other vectors, okay, because you knew that. Okay, so we'll talk about insulators and conductors. We'll talk about electric insulators and electric conductors. What is the difference between the two?
One's good at conducting, one is good at
Conducting what?
electricity.
Yeah, okay. So you have electrical conduction, you have thermal conduction, and so on and so forth. Okay, so we're talking about electrical conduction here. And so if you, here's what we're talking about. You take a wire or that material, and if it's a good conductor, it will let a current pass through, and if it's an insulator, the current will be zero or very small. So you take a piece of wood, connect it to a battery, and there won't be any current. You take a piece of copper wire and you connect it to the same battery, and you get a nice current going through it. So the question is, what is the difference? What is the difference between these two materials? All right. Now I'll briefly tell you what's going on. Okay, so in a good conductor, there's a simple picture is there's free electrons, okay? And the free electrons are like the gas in this room. You set up an electric field in there, and they will move freely in response to the electric field. All right. So now we'll give a little more detailed picture of that. That's the simplistic answer, okay? So you have to be a little patient here. All right, so here's a single atom, and we'll just draw lithium. Okay, it has there's the lithium atom, and all these electrons are arranged in energy levels. Okay, so here are the energy levels of the lithium atom. Okay, every atom has these energy levels. Okay, so the lowest energy level is occupied by 2 electrons. Okay, so you guys know all this. Okay, now here's what we're going to do. So now let's say you put together a solid. Okay, so you take copper atoms, a whole bunch of copper atoms, and put together copper. Okay, and the atoms will arrange themselves like this. Each copper atom will give up roughly 2 electrons. Okay. And these 2 free electrons are free to move about. Okay. So those copper became ions in fixed locations. Now, why do you think they did that? Why did the copper atoms give up their electrons? And it's nature always wants to go in a more stable state. Very, very good. Okay? So that's what happened. This is a more stable configuration. And now let's look at what happens to these energy levels. Okay, these are the energy levels of the single atom. Okay, when you put together a solid, let's say when you put together 1 billion atoms, each of these energy levels become a band of energies. Okay, this was a single energy level for a single atom. Now if you put together 1 billion atoms, that becomes 1 billion energy levels. Okay, so now you have a band structure. Okay. So this became that band, this became this band, and this became this band. And so this is what you'll study in solid state physics if you become a material science engineer. Okay. Now, so this is the lowest band. All this band is completely full, completely full, completely full. And so if you have full bands like this, there's a band gap and this band is empty. That's an insulator. There's no electrons to conduct. In the topmost band, this is called the conduction band. You need to have a partially full conduction band. That will be a good conductor. In an insulator, the topmost band is completely full and the next band is completely empty. You want to make it, you want a conducting material, what you want is some electrons in the conduction band. Okay? Okay, so a partially full conduction band allows electrons to move about freely. So, okay. So that's the rough picture. Okay? That's a 30-second view of what's going on. And now if you take such a material and connect it to a battery, okay? So in a conductor, like you saw, there are free electrons. Now I'm just drawing the free electrons. I'm not drawing the background positive charges, okay? You learn that when you connect a battery, what this battery does is it establishes an electric field inside the conductor. And now, since you have free electrons, these free electrons will respond to this electric field and move in the opposite direction. And that's a current. Now, if you don't have free electrons, you can't have a current in that material. Okay, that's what's going on. All right, so again, we just, you will eventually learn all of this. Okay, we just took an extra tour, so to speak. Semiconductors are material whose electrical conductivity is in between that of insulator and metal and conductors. Okay, and in addition, you can control their conductivity. You can make them more conductive by adding impurities. Okay, so all right, we won't worry about this. Okay, so now you're already experts. I have two positive charges. What will they do? They will repel each other. Oops. Okay, so Mr. Coulomb answered, what is the magnitude of this force? Okay. And here's what he found, Mr. Coulomb found. This is the Coulomb's constant, Q1, Q2, divided by R squared. Okay. So the magnitude of the force is given by this formula. It's proportional to the product of the charges. There's a proportionality constant, and we've named it that constant in his honor, divided by the distance squared. Okay, so what Mr. Coulomb found was if you double the distance between the charges, the force falls by a factor of 4, reduces by a factor of 4. All right, now I'll briefly explain how Mr. Coulomb found this. Okay, so what he did was, here's a wire, and he had two spheres there. Okay, so again, here's the wire, there's the wire. This is an insulator, and you have two metal spheres there. Okay, now the property of the wire is if you twist the wire, it'll oscillate. What if the wire is stiffer? What will happen to the oscillation?
Faster?
Very good, my friend. You earned your $1. I won't take it back. No. Right, so the torsion constant, again, stiffer the wire, higher the torsion constant, and the faster it will oscillate. The harder it is to twist the wire. Okay? So now what Mr. Coulomb is going to do is he's going to put charges on these guys and then bring another sphere with charge there and here. Let's say these are negatively charged and you bring positive charged spheres, what will happen? This guy will attract him, this guy will attract him, the wire will twist, but you know how much force it takes to twist the wires. Okay, so that's how Mr. Coulomb found this magnitude of this force. Okay? And so the magnitude of the force is proportional to the product of the charges divided by the distance between the charges squared. Okay? That's the Coulomb constant. And when you do your engineering classes, yeah, well, that's 9 times 10 to the 9. That's a large constant, and so that's why the electrostatic force is a large force. Okay. Now this Coulomb's constant is expressed in terms of the permittivity of free space. A lot of engineers use that, so you want to know that. Okay, so we'll write it as Coulomb's constant, the subscript E, so that you don't confuse it with the Boltzmann's constant that you used the last 4 chapters. Okay. And that's 1/4 pi epsilon naught. Okay, again, epsilon naught is the permittivity of free space. Now, this Coulomb's constant, again, this is very similar to the force of gravity between 2 objects. The only thing is gravity is always attractive, okay? And the force of gravity, you guys remember, was G times m1, m2 divided by r squared. Product of masses divided by the radius squared. The formula is exactly the same, except that this gravitational constant is very small. Okay? So gravity is a very weak force. Okay? That's illustrated here. Okay? So what this says is the following. So this is the hydrogen atom, which has a proton and an electron. Okay. Okay, this is positively charged, negatively charged, so there's an electrostatic force. There's an electrostatic force. Well, they have masses too, and there's a gravitational force between the two. Okay. So what we are going to show you is this electrostatic force is very large compared to the gravitational force in this hydrogen atom. Okay, so in the hydrogen atom, the electrostatic force is that many newtons, a billionth of a newton, well, 100 billionth of a newton, and the gravitational force is that tiny. Okay, if you take the ratio of the two, the electrostatic force between these two guys is 10 to the 39. That's 1,000 trillion times stronger. Okay. So pretty much what we are trying to say is whenever the electrostatic force is talking, you can ignore gravity. Okay, so it's that much stronger. Yeah. So that's why whenever you do your chemistry classes and stuff like that, you know, we only talk about their charges and stuff like that. The forces that are relevant in atoms are only the electrostatic forces. You don't even talk about the gravitational force. Okay, here's a second example. Okay. Remember we talked about you rub the balloon against the wool sweater and some of the electrons go from the rub wool to the balloon. It's a very tiny fraction. It's very hard to remove a whole bunch of a substantial amount of electrons. Okay. So here is an example illustrating this. So this is about a kg of water. Okay. If you took another glass like this, another kg of water here, now this is impossible to do. if you strip this water of all its electrons, again, impossible to do, and strip this bottle with all its electrons, put them 1 meter apart, this is positively charged, this is positively charged, they'll repel each other. The force of repulsion between these two guys will equal the weight of the earth. That's how strong the electrostatic force is. Okay. If you take two 1 kg blobs of protons and set them 1 meter apart, the force between them would equal the weight of the earth. So the electrostatic force is a very strong force. Okay. And anytime in nature you separate some charges, okay, nature will neutralize those charges. You see this during thunderstorms. In thunderstorms, because of the turbulence and all, those water molecules rubbing against each other, just like when you walk across the carpet, charges will separate in the cloud, and you have lightning neutralizing the charge. Okay? That separated charge doesn't stay separated too long. Okay. All right. So the electrostatic force is a large force. Okay, this is the superposition principle. So let's say there's a bunch of charges floating around. Well, so you ask, what is the effect on this fellow? Well, this guy is attracting him, this guy is repelling him. The net effect on him is just the sum of all the forces acting on him. Okay? And the superposition principle says you can't tell if there's one single force acting on him or hundreds of forces acting on him. Okay? So he behaves as if a single force, which is equal to the sum of all those forces, act on him. Okay? Okay, and this is true no matter how many charges are there. So the effect on this guy is equal to the sum of the forces due to all these guys. Okay? Okay, in nature there are only 4 forces. The strong force, the electromagnetic force, the weak force, and the gravitational force. And these are the relative strengths. Okay, the strong force, if we say, let's say the strength of the strong force is 1 unit, the electromagnetic force, we are talking about the electrostatic force, but the electromagnetic force is 100 times weaker. Okay, so this will explain the following fact. So we'll draw the carbon atom. Well, I'll draw the carbon nucleus. So what does this symbol mean? It has 6 protons and 12 is the mass number, so 6 neutrons and 6 protons. Okay. 1, 2, 3, 4, 5, 6. Okay. So here is the carbon nucleus. And the question is, I've been telling you for the last 15 minutes that the electrostatic force is very strong. These guys should be repelling each other. So the question is, why aren't they flying out of the nucleus? The protons, why aren't the protons flying out of the nucleus?
Because they're balanced with the electrons?
What's that?
Because they're balanced with the electrons?
No. Well, I mean, these guys are in. What's that? Well, so these guys should be flying out and you shouldn't be stable at all. All right, so here's the answer. Okay, so that's a strong force, but there's a stronger force holding them together. The strong force there's a strong force that is 100 times stronger that's holding them together. That's an attractive force. And that strong force is equal between neutrons and protons and stuff like that.
What's causing it?
What's that?
What's causing
Okay,
this?
so the strong force is mediated by gluons. Okay, so in the quantum theory, all forces are mediated by these particles, bosons. Okay, so the strong force is mediated by gluons. The electromagnetic force is mediated by photons. The weak force is mediated by these guys. The gravitation is supposedly mediated by gravitons. We've not discovered them yet. We've not
So-
run into them. Yeah.
In a particle, you have like the proton, like the electron, the gluons, are they invisible or is it just like,
Yeah, so they are,
what are they attached to? What are they attached
so all these are fields. They, when these particles attract each other, they exchange virtual particles. So when a proton attracts an electron, it's exchanging virtual photons.
to? Okay.
But, okay, they'll take real forms as well, okay. Now here's another mystery that you will answer, okay. So now you see why these protons are not flying apart, because there's a strong force that exists that is 100 times stronger than this. Okay, but let's answer another very interesting mystery. Okay, the strong force is 100 times stronger than that. Well, the electromagnetic force has an infinite range. Okay, you can have two protons as far apart as you want, and they'll still want to repel each other. But the strong force, the range is only 10 to the minus 15 meters. So you take a proton, if this is 10 times 10 to the minus 15 meters away, what happened? Now the strong force is gone to zero, and only the electromagnetic force is acting. And they'll fly apart. So what does that mean? That means a nucleus, all nuclei are roughly 10 to the minus 15 meters in size. Okay, so whenever you want to put together a nucleus, okay, this is roughly 10 to the minus 15 meters apart. Yeah. All right. So the size of all those nuclei, about 100 different nuclei, are roughly that. Okay. All right, so that's what this table is saying. This is telling you the relative strength and the range. Here's a weak force that's 1,000,000 times weaker than the strong force, and that's why it's called a weak force. And its range is even smaller, 10 to the minus 18 meters. Okay, and the range depends on, so these are massless. These are massive particles. Okay, so they're exchange, and these are massive, and that's why the range is so small. Okay. So in nature, there are four forces. Okay. These are four forces at low energy, at our existing energy. At higher energies, all these forces were combined, believed to be a single force. Okay, so I'll give you an example to think of this. All right, let's take this material H2O. And I have it at 200 degrees Celsius. What do you have?
Yeah, so they,
Steam, right? Gas, okay? Now, I'll reduce the temperature of this, and I'll bring it to 100 degrees Celsius. What happens?
It's still gas unless you take more energy from it, right?
So, yeah, so then you get liquid and gas. Okay? So as you decrease the temperature, as you decrease the energy, this single phase, you got two phases. Just like that, at higher energies, all four forces were a single force. And as you lower the energy, you get the forces separate. Okay? So that's the belief. And that's what's shown in this graph. Okay. So, so this is the average energy of the particle, and this is the temperature of the universe at these times. So 10 to the minus 50 seconds after the Big Bang, the temperature was somewhere there, and all four forces were a single force. Okay? And as you cool down the universe, as the universe progressed, as time passed after the Big Bang, the first force to separate was gravity. Okay? And after inflation, the strong and the electroweak forces separated. See, the universe is cooling down. Okay. So the average energy is 100 giga electron volts. The mass of a proton is 1 giga electron volt. So this is 100 times the mass of the proton. Again, I'm just telling you a story. Okay. Here's quark confinement. So at these temperatures, all the quarks were free. The proton and neutron had not formed yet. At this point is when protons and neutrons formed. That's what that is. Okay. Do you guys know what is deuterium? What is deuterium?
It's like hydrogen.
It's an isotope of hydrogen. Very good. Okay. I almost thought about giving you $1, but I won't. All right. So it's a isotope of hydrogen. Okay. Now to split this guy, you need photons of about 2 MeV. Okay. So if on the average, if the energy of the photon is greater than 2 MeV, this cannot form because this photon would hit that and split it. Okay. So what this graph is telling you is it's got lots of information. As the universe is cooling down, at this energy, quarks, protons, and neutrons were formed. At the universe is still cooling down, the average energy of the particle is decreasing, deuterium can form. The deuterium nucleus can form. Okay, and that's what it's saying. The universe is still cooling down, transparency point of light. So this is 400,000 years after the Big Bang, and now the hydrogen atom can form. So to form the hydrogen atom, so here's the hydrogen atom. Okay. Do you guys know the energy of the hydrogen atom, the ionization energy of the hydrogen atom? What is the ionization energy of the hydrogen atom? 13.6 electron volts, okay? I'm going to ask you this next Monday, you'd better remember it, okay? So the average energy of the photon, I'm not kidding you.
I'm not, I bet you.
All right. So the average energy of the photon is less than that. And now the hydrogen atom can form. Okay, so, and that's, so you see that microwave background radiation? So that's the radiation that's cooled down. Okay, Eli, you had a question, my friend.
Yeah, so like basically like the first half of that graph happened in less than a second.
That's right.
So they call them eras, but really, it was very, very short eras, right?
Yeah, well, yeah, different phenomena happen, and it's amazing. This little picture is pretty amazing. Okay, you go and carefully study this again. This is the Big Bang, And you see, this is our present era, and the microwave background radiation that you're bathed in, the average temperature is 3 degree Kelvin, 2.73 and change. Yep.
So would tritium be able to produce before deuterium?
I'm sorry?
Tritium?
Yeah, tritium. Yeah.
Tritium would be able to produce before deuterium?
No, it'll probably is less stable than deuterium.
Let's say.
Yeah, I'm not sure. Okay, but these guys are. I mean, these guys are bigger mileposts, and that's what's been. Okay. All right. So again, so protons and neutrons are made of 3 quarks. Okay. Now there are no free quarks in the universe. Okay, but if you lived here at this time, you could be swimming in free quarks. Okay, so you would have had a quark gluon plasma. The best you can do now is electron proton plasma. You go to the sun and you have an electron proton plasma. Okay. Yeah. All right. Did somebody else have a question? Okay. All right. By the way, guys, so if you ever need a break, let me know. There's 43 slides to this chapter, and I am going to finish this lecture today. Okay. So you get tired and you can't concentrate, let me know. Okay. Here's an interesting fact. So we have 2 kinds of charges. Okay, positive and negative charges. Here's a proton and here's an electron. And the proton is about 2,000 times heavier than the electron. The electron is a fundamental particle. It has no substructure as far as we know. This guy is substructure. It's made of three quarks. Okay. It's 2,000 times as massive as this guy. They're not in no way are they related. But their charge is exactly the same. To how many ever decimal places you want. Their charges are exactly the same to how many ever decimal places you want. I mean, this is what we measured. Well, how do we know that? Okay, so you can go outside, pick up a handful of dirt, and you got a whole bunch of protons and a whole bunch of electrons. The exact same numbers. And that dirt is always neutral, no matter how big a fistful of dirt you pull. Okay? So again, that's pretty amazing.
Does that mean the universe is neutral?
Yeah. As far as we know. Okay? Very interesting, right? Another thing what we found is charge is quantized. Okay, so if something is charged, what we found is, so here's the smallest charge, and the total charge is always an integer multiple times the charge. Okay. Now it turns out that quarks have fractional charges. These guys have half E and stuff like that, except that you cannot go to a store and buy a quark by itself. It always comes inside a proton or at these energies that we live in. Okay? If you wanted to go buy a quark by itself, where would you have to go?
Go forward around like 10 to the negative 30.
So a billionth of a second after the Big Bang. Okay, which is called an era, by the way, my friend. Okay. So, well, it's multiple eras actually. Okay, so again, many interesting stories. Okay. So charge is quantized. Okay. And Mr. Millikan was the person who discovered that charge was quantized. Okay, and here's the experiment he did. Okay, so here's an oil spritzer. You spritz oil drops, and when you spritz, the friction, just like when you walk across a carpet, the friction will charge these oil drops. Okay. Now, So Mr. Milliken lets these oil drops drop, okay? And it turns out that, so right now we don't have any electric field, and even if they're charged, they're only falling under the influence of gravity. And heavier the oil drop, greater the terminal velocity. Okay? So Mr. Milliken is looking at them through a telescope, and he measures the terminal velocity. From the terminal velocity, he knows the mass of the oil drop. Okay? So he's measured the mass of the oil drop. And also, if he wants, he can shine X-rays on them and charge the oil drop. Okay? So now he knows the mass of the oil drop, and now what he does is, let's say he charges this with a negative charge, and then he connects a battery, it makes this plate positive, negative, and the field is in this direction, and the particle will be attracted in that direction. So what he's going to do is balance the electric force with the gravitational force. So here's the oil drop, there's the electrostatic force on it, here's the gravitational force on it. And apparently he studied millions of drops. Very patient fellow, him and his assistant. And he's measuring the charge every time, okay, because he knows the mass of those guys. He knows the electric field. Okay, and the charge is the weight of the oil drop divided by the electric field. And what he finds is this charge is every time, it's an integer multiple times the smallest charge. Yeah. So that's how we learned that charge is quantized. Yep. All right, so we'll go through these 3 slides and then we'll take a little break. Okay, so here's a factory spewing out smoke and stuff like that. And if you're poor and you live close to the factory, you'll have chronic bronchitis and stuff like that. Of course, we want to clean up this smoke. Okay, so how do we do that? So here's something called an electrostatic precipitator. So for instance, you would have this near a thermal power plant and all that. Yeah. So what these are metal plates. So these are metal plates. Here's a side view. And these are wires coming out of the metal plate. So again, I'm recording this, but so here are the metal plates. Okay. And here are these wires. Yep. And what we're going to do is we're going to connect 25,000 volts between the wires and the metal plate. So the wire is negatively charged, that's what that's showing. Okay, so we'll connect a large voltage. $30,000 volts, let's say. Okay, and then what we're going to do is pass the dirty smoke through here. Now this wire, it's at negative voltage, it's going to spit out electrons. What do the electrons do? They go and attach to the smoke particles. Now the smoke particle has become negative. What will it do? It goes and attaches to the positive plate. So all the smoke particle attaches to the positive plate. You can remove 99% of the particulate matter, 99.9%.
Where does it go though, once it attaches?
Okay, so it attaches. What do? A whole bunch is attached to the metal plate. And then every once in a while you shake them and collect it.
But it's still smoke. But the smoke is still there, like it exists.
No, you removed all the particulate matter from the smoke.
Yeah,
So that's all that matters.
Yeah. And now the other hot air carbon dioxide and all can go away.
Like a water filter.
What's that?
It's just like a water filter.
Yeah, it's just like a water filter. Okay, now we had to force the companies to do it. Why did we have to force the companies to do it?
Because they don't want this.
It's expensive. It's always that. Okay, in a thermal power plant, about maybe 2% of your electricity. So for every dollar you earn, 2 cents, it costs you 2 cents to clean the air, something like that. Yeah. Okay, so here's something that you guys use all the time. Okay, so there's something called conductive materials. What do you think that might mean?
Conducts through light.
Yeah.
So there are these materials. Remember, what was the difference between insulators and conductors?
Conductors
Insulators are good when you
charges to
Yeah, so conductors had free charges in the conduction band, so to speak. So we'll loosely speak.
and inductors not.
And insulators, all the charges were held tightly. So there are these photoconductive materials. If you shine light on them, they release these electrons. So now you have free electrons.
In the air.
Well, within the matrix. Yeah. And if you keep the material in dark, there are no free charges, and now they're insulators.
It's like a higher frequency light, isn't it?
Well, yeah, no, you can do it with visible light. Okay? So photoconductive materials are in the dark, they'll be insulators. And you shine light on them, they become conducting. Okay. So,
Is this helpful with like solar panels or?
no.
Yeah, I watched the experiment on this, and they shot a laser at it, and they kind of showed it as like pool balls getting kind of pushed away from, that's kind of how they explained it, but they had a laser that they shot at something that was charged, a balloon,
Mm-hmm.
and it dissipated the charge.
Okay. All right, but where the heck is my material? Selenium is such a material. It's a photoconducting material. All right, so here's a metal drum. We'll dust it with selenium, and you ionize the selenium. So you strip it of its electrons. This is all in the dark. Okay? Selenium is an insulator in the dark, and it's not losing its charge. Now you're going to make a photocopy of this. You're going to shine light. Wherever light fell, selenium became conducting. All that got neutralized. Wherever it was dark, it's still charged. Then you go and get toner, negatively charged toner, dust the drum with it. So now you have a dark spot area here. You get a paper, warm it, get the paper positively charged, and roll it over the drum. All the negative toner will come over it.
This is how our normal printers work that we use.
That's how your photocopier works, yeah. Mm-hmm. Now your laser printer, instead of shining light like that, you scan the laser and turn it on and off at the right time. Okay. See, amazing technology. Okay. Okay. I don't know if you guys remember inkjet printers. Some of you probably have never seen an inkjet printer. Do you know what an inkjet printer is? No. All right. So drops are shot from a generator, about 100 drops per character. So if you printed this on an inkjet printer to draw this P, you would need 100 drops of the inkjet. Okay, so here's this generator that's spitting out ink drops, and there's the paper where you want to print it. So let's say you want to print a C there. Okay, so let's say what this plate, we'll talk about this in a later chapter. You make these two plates this plate positively charged, negatively charged. You shoot an electron, the electron will be deflected here. Okay. Now, this is an ink drop. Let's say you give it more negative charge, then it'll deflect more. You don't give it any charge, it goes straight. Okay, so you want to print something here, you don't put any charge on it. You want to print something here, you put a lot of charge on it. Okay. All right, so to draw a single character, you're using 100 drops. On these 100 drops, if you want to draw the character there, you're putting a lot of charges. If you want to draw the character here, you're putting less charge. That's what your driver is doing. Deciding how much charge to put on that ink drop. And all that is happening very fast. All right, we